So these are the main points. Basically, three types of discrete random variables, and we go from here to everything else in inversion. And the geometric random variable, I said, is special, just like its cousin in the continuum, which is the exponential lambda random variable. And I said they are memoryless because of a very special property. We will see this property when we try to model the waiting times between New Zealand earthquakes soon. It's kind of a simple model that traffic engineers use to model, say, arrival of buses, for example. So this is the probability density function, or PDF. It's lambda e to the minus lambda x if x is greater than or equal to 0 and 0 otherwise. And the distribution function is 1 minus e to the minus lambda x. So the PDF looks like this. So lambda e to the minus lambda x. Right, so if lambda is big, it goes higher. And then because everything has to integrate to 1, it'll be more spiky. And the expectation of this random variable is actually 1 over lambda. Right, so that's some intuition. The Poisson random variable, which is actually, you have seen the Poisson random variable before, right? Yeah. The Poisson random variable is also constructed from Bernoulli's, right? Does anyone remember how that construction goes? So we saw the binomial construction once in class before, right? Yeah. So basically, you have a sum of independent and identical Bernoulli theta random variables, right? And then you basically have the binomial coefficient. And I drew this picture of the Galton squint chunks, right, with nails. The number of paths. So 0 is left turn, 1 is right turn. The number of paths to get to a bucket, which counts the total number of right turns, right? Total number of ones in a sequence of length n made up of zeros and ones. Right? So we said there are many paths to come to a particular number of ones, and that's what the binomial coefficient accounts for. So the construction for Poisson, I mean, just sort of intuitively is like this. So we have, so you can imagine the Galton squint chunks like this, with the nails and so on. And then there are the buckets in the bottom, right? So this is binomial, right? So this is bucket label 0, no right turns, 1 right turn, and so on up to n right turns. And there'll be n levels, right? Level 1, 2, and so on. So now imagine taking the squint chunks and letting n go to infinity, right? Just imagine. And then you control the probability of right turn by sort of turning it tilting the whole thing this way. So that's really the construction, right? So you want theta. Theta will get smaller and smaller if you tilt it more and more this way, right? Because it'll fall to the left. So you just want theta to get small at the right rate, right? So as n goes to infinity, you want theta to go to 0, okay? With the right condition, it outpops lambda. So lambda becomes the parameter. We will see this, I think, in detail soon. Sorry, I don't want to get too far into it. But that's how you think about the Poisson as a limiting process of the binomial sum of Bernoulli's. Okay. So what is the connection between exponential and Poisson? If events are arriving according to this Poisson distribution, so you have, say, a unit interval or a unit interval of time, and then you ask something is arriving such that the time between arrivals is exponential, right? So let's say I'm at a bus stop or something, and the time between arrivals, so I go here, so time 0 is when I reach the bus stop. So then I wait, okay? Or I just observe at the bus stop. So the first bus comes at this time. So then if you call this, say, x1, and if you say x1 is exponential lambda, and then, after a while, maybe the second bus arrives fast, this is x2, right? And so on. And this is also independent exponential lambda. This is also another exponential lambda random variable and so on. And let's say I'm sort of looking at 1 hour, right, or whatever, or say 10 hours. And then I wait, and then I see how many buses arrive. Right? So the number of buses that arrive, it will be Poisson distributed, number of arrivals is Poisson, the parameter lambda. And the connection is that if the inter-arrival times is exponential lambda, then the number of arrivals is Poisson lambda. So there's this other basic connection from probability. That's kind of what I'm trying to remind here. Okay, so while we know this, if x is 3, x is how you get the exponential. And here is just some functions for the PDF and CDF. Okay. And I'm careful not to use LAMBDA here, right? Why? Because there's a keyword, right? Remember the lambda expressions for anonymous functions we saw? So if you want to write a function without the name for the function, right, we use the keyword lambda. So I don't want to overwrite it, right? Because I overwrote line before, right? So you try not to. I mean, the good habit is to actually use capital letters to begin with parameters, but well, anyway. So that's the reason I don't want to, shoot myself on the lambda expressions later, so if I need them. Okay, so here's just a little interact. You can just see that's what I drew on the board. If you increase lambda, this guy is going to get spikier, right? And yeah, so that's the CDF. Okay, so so you can show this. It's just solving a single equation. So if you do the following, if you take if you set u equals capital of f of x lambda, okay, and then you solve for x in terms of u, you will get the inverse, right? So this kind of thing I expect you to be able to do, say, definitely in the exam. I might give you a random variable with some density that I cook up, okay? I know that I can invert it because I tried it before. So you have to, you can invert it. Either you can do it by hand, it will not be too complicated. So that's why you should have some paper and pencil in the exam, in the computer lab. But I think there are methods of doing this symbolically downstairs, I hope. So you can also do it directly in Sage Math. Okay. So the inverse distribution function is -1 over lambda, ln of 1 minus u. Right? You just apply logarithm and move the lambda, basically. So our pseudocode is the same principle, right? It comes from this inversion algorithm. So u is uniform, f inverse of u is what you need to find the expression for, and then you need the parameter lambda, and then you can output the sample x from exponential lambda random variable. This is exactly the algorithmic steps. Okay, so it's just like Groundhog Day. As long as you figure out what the inverse is, it's the same idea. So here I'm implementing this function, exponential f inverse, and then, so this gives me f inverse, and then I make a function called exponential sample. So I want n samples with parameter lambda, and I have u's, and then I do a list comprehension with the inverse distribution function. Okay. So let's have a look at a small set of samples with lambda half, so 30 samples. So in Python 3, this will change to, so you have to put like parentheses around prints, but Python 2, you don't. So this doesn't harm Python 2 either. So that's just printing. And I've sorted the samples, okay? I got a bunch of samples and then I just sort them. Okay. Yeah, so this is sort of fair game when I ask you to simulate in assignment or exam. So this interact just sort of shows us, let me just see, we know the sample should be concentrated, so if I increase the sample size, it's going to get more and more curved. Let me increase the bin size, so I see that looks a bit jaggedy. Let me increase the sample size. Yeah, so it looks like the PDF, okay? So how many of you know about the standard Cauchy random variable? So you should have seen this when you got introduced to central limit theorem, hopefully. Okay, so this is like a classic counterexample of how central limit theorem will not work. This is an example of a random variable that it violates the conditions in the theorem. So this is the density function for Cauchy. F of x is 1 over pi 1 plus x squared, and x is anywhere on the real line. And its distribution function, when you integrate it, is 1 over pi tan inverse of x plus half. Okay, so obviously you'll have this notebook in your exam, so you don't have to memorize it. But this is the punchline, right? The Cauchy distribution is an interesting one because its expectation does not exist. Right? So when we define the expectation of a random variable, we first of all, have to assume that it exists. So expectation for continuous random variables is just the integral. Right? So what we mean by the expectation not existing is if I take the integral of the absolute value of x df of x, right, and chase it down, I get infinity. So I need this. I can't have this, right? So it has to. Well, it's infinite. The expectation is infinity. So then we say that it does not exist. So in Sage Math, we use arctan for tan inverse and pi for pi. And we can code the PDF and CDF for distribution function for Cauchy like this. And we can just look at how the PDF, that looks kind of like normal, right? I mean, doesn't it? Like it's sort of centered at 0, it's decaying. And it looks like the CDF of Gaussian, right? Normal. But what's strange about Cauchy is that the tails don't decay fast enough, right? The tails just are like fat. There's a sort of fat tail or heavy tail is the terminology. So that's kind of the problem with Cauchy's density, right? It's still still a valid random variable. So the construction of Cauchy is geometric, actually. So it's this is my construction, So do you guys know Darth Maul in Star Wars? The double-edged lightsaber. He was my favorite. I don't know. My aunt thought I was demented. Anyway, he's cool. So imagine taking Darth Maul's lightsaber and putting it at 1, 0, right? And then now, we're gonna sample theta uniformly from 0 to 2 pi, right? Circle. So, and then that's the construction. So this is theta. So once simulating a theta and fixing this to be theta just means spinning it and letting it come to rest. So sometimes, it's uniformly distributed. So if theta is this value, the lightsaber will be like this. So you can imagine the laser beam shooting all the way. Right? So then it intersects the y-axis at x1. So then you say that's a realization of Cauchy. That's how the construction is done. So you can kind of chase it up more. And then sometimes it will rest like this, and then x2, will be the second realization of Cauchy. But the punchline here is, the probability, because any small degree, in interval of thetas I choose, and I move that interval around the circle, right? It has the same probability of realizing in that tiny interval. So that means this lightsaber is very likely to hit the north pole and the south pole of the circle. Right? You won't exactly hit it, right? It's continuous, but say it's slightly left or slightly right. It's going to touch the y-axis either very close to positive infinity or very close to negative infinity. You see? Now you start seeing the problem, right? If you do cumulative sums on this, it'll kind of be like pretty good for a while, and then boom, it's going to take some huge number and take you totally off. So the cumulative sums, or the running means, will never settle down for Cauchy. Right? And if the cumulative sums don't settle down, you basically busted for central limit theorem, right? Central limit theorem is all about the running means, or averaged cumulative sums. Okay, so that's kind of the intuition. And so it's good to have Cauchy around to like make sure we know the limits of the theorems we will use soon. Okay, so yeah, so this you can find the inverse distribution function for Cauchy. So this is just sort of done this step by step. I mean, in the exam, you just have to find the right answer and use it, right? So, but this is basically how you can work it out. So I solve for x in terms of u. So now I have x equals tangent of u minus half times pi. So that's my inverse distribution function. So same algorithm. I just put this guy here, and voila, I have Cauchy f inverse of u. I'm returning RR. This is just because I want to be in multi-precision floating point reals, because I might just need all the precision I need, okay? I might have to have. And then I just put this here. And then my Cauchy sample just takes u's and does list comprehension with the f inverse as before. Okay, so here's my sort of interact. So this is how the Cauchy samples look. First 50 Cauchy samples, between minus 12 and 13. Let's sort of see what happens. Whoa, look at that. So 2,580th sample is boom, minus 8,883. Right? So and if you keep increasing it, it's going to do this crazy stuff. Okay, these are all, every time it's generating a new sample, so it's not building on stuff. So that's kind of the point with Cauchy. Okay, so let's now, we know how to sample from it, so let's actually do a little interact, and then I just have lower and upper bins here, and this is how the normalized histograms look. It looks like the density, but if I increase the number of bins and maybe make the lower and upper things a bit wider, you're going to see strange tail behaviors. Okay, it looks like the sampler is working. So we've seen running sums before. This is using NumPy's. So from PyLab we import CumSum, PyLab, NumPy, same family, and then I have the samples generated as 10. Theta 1 and theta 2 are 0 and 10, and this is for the uniform 0, 10 random variable. So let me just get 10 samples from the uniform 0, 10. That's there. And clearly we can just get the CumSums. So the first object is the final cumulative sum, or the sample mean. That's 1 over n. But then we can do this just list of CumSum of the u sample. Get this. Okay, so that's basically what we have in the list. And then I'm going to do, because I only one sample, I divide by 1. Here I have 2 samples, I divide by 2. So this is essentially called the running mean, right? So the behavior of the running mean is the whole point of central limit theorem. Right? So what I mean by behavior of running mean, that means if I repeat the experiment again and again with multiple running means, what is the distribution of the running means at any end? Right? The central limit theorem says something about how that is distributed. Okay, so yeah, we can do these divisions. We've seen this before, and then I have my uniform running means now. So if you look at the uniform running means, they should be roughly around half, right? Because this is a 0, 10, so it's 5. This is 0, 10 uniform distribution, so half is the mean. So that's that. Now let's turn this into a function, and so I have a function for uniform running means, and I can plot them. Right? So there we go. So here is basically doing this. Now, n to generate is how many samples to generate. Iterations is 5, so I want to repeat the whole thing 5 times. So I have 1 uniform 0, 10 running mean, another one. So I have five such iterations. So what we're really interested in is, if I take a slice here, what is the distribution of this as the number of iterations go to infinity, right, for fixed n. And then also n is going to infinity. Okay. Yeah, so I'll let you do this utry, write a function. So here we have a slight exercise for you. So I've done just the uniform 0 to n running means here. Your task about in the utry is to figure out what the picture should be for the Cauchy's running mean. Okay, because you already have all the components. You know how to sample from Cauchy, and then you just have to figure out how to do this. And if you get stuck, so please don't look at the solution. This is just to kind of get you prepared for the exam. So if you get stuck, here's the answer in the bottom. Okay, so okay. So what you will realize, we revisit this again, is that this guy's running means will not settle down. They will kind of go like this, and boom, they'll just go all over the place. Okay. So yes, this is about replicable samples, right? So if you produce samples, you want to replicate exactly the same sample, then we use the set random seed, right? So this is how we control this. So, yeah. And I think this is out of place, so we've already seen about default parameters. If you use equal to something, and if you don't specify what y is, it'll take the 0 value. So, we should make a note. Okay. Yeah, so this is basically playing with defaults. Yeah, so do this utry as well. So this is telling you about the type none type, and it's a special Python type. So so if you set seed random seed to none, then yeah, it'll have its own initial seed, and then you can ask what it is, for example. Yeah, so if you do this again, it'll be a different random seed. So when you don't say none, that's what's really going on when you put nothing in the parentheses, right? So because sometimes you'll do a simulation or whatever, and then something will work, and then you really want to maybe save the seed because you want to use it to build intuition, right? So this is helpful. Okay, so here is another utry. It's a simple simulation. And the idea is that, so in New Zealand, we have this bus called the Orbiter. I think you guys have something that orbits around the town, right? What is the bus? It just kind of goes around.
One.
Huh?
One.
Oh, one, yes, number one. It's a good number. So Orbiter is what this one is called in Christchurch. So it's a bus that just goes around the city. And so, you know, so when I taught this, not this course, it was so different several years ago. In New Zealand, like students did projects, and you know, we're only like 20 students. So one of the students was Josh Fenmore, and what Josh did was I actually sponsored his beer. So, you know, we wanted to collect real data, right? So it was hardcore applied stats. So we actually never loaded any libraries at the time. So, so he needed to sit at this, not at the bus stop, but there was a student cafe or pub, I don't remember. And so he could observe the buses from this nice warm place. So he was just sitting there and observing, right? So here's the bus stop, and buses come, right? So orbiter buses, they come in both directions, right? this bus stop. And he uses recording time. Okay. And he actually collected a lot of data. We probably will use his data later on. And then the main punchline here was Orbiter guarantees Christchurch residents that the average waiting time between the arrival of buses is 10 minutes. Okay. So, well, okay, is that really true? Because some people are like, well, no, this is not true. Every time I go to the bus stop, they know, mean to me. I don't know. Depending on how your brain is at the time, you have all sorts. So we really want to do a hypothesis test. And that's what we will build on in the course actually as well. So the simplest hypothesis test was this, lambda. So the model was this. X1 through Xn is independent and identically distributed according to an exponential random variable with a parameter lambda. And of course, you don't know what it is. You just have the data, right? So then he wanted to know, so 1 over lambda is the mean, right? So the expectation of the exponential random variable, the population mean is 1 over lambda. So if this is actually closed, so the question is this close to 10 minutes? So this is all in units of minutes. That's the question, right? And you don't want to just go and yell at people, right? So New Zealand civil servants have zero tolerance policy. You just can't go and yell at people in the office. So if you want to make a complaint, you usually use some scientific principles, or in management lingo, it's called evidence-based reasoning. So what we want to do is hypothesis testing. So this is how testing, and before that, parameter estimation. So we want to find out an estimate. Usually in statistics, you put a hat over the thing you're estimating, okay, with the data. So you do parameter estimation and find out what an estimate of the unknown lambda is. And then when you do that and know a bit more about central limit theorem and stuff, then you can test the null hypothesis that lambda is equal to 10. Or 1 over lambda equals to 10. Yeah, lambda equals 1 over 10. Same. Okay, so this is the null hypothesis you were trying to reject, right? Because I told you guys about Popper's falsifiability and demarcation of science from non-science, all of that. So in your attempt to reject the null hypothesis, if you succeed, well, then you rejected the null, right? But if you fail, then you haven't. So this is essentially kind of coming attraction. So we'll get into how to do this, both in parametric settings where lambda is a fixed parameter, and the distribution is specified by just finitely many parameters. In this case, it'll be one parameter. I mean, but this one unknown parameter can take any real value greater than 0, right? Because that's where lambda lives. Lambda's parameter space is 0 infinity. So it can take any positive real number, but you don't know what it is, but still it's only one dimension. And the theta 1, theta 2 example, there are 2 parameters, right? So it's 2 dimensions. But even if there are only k dimensions, k is less than infinity, these are called parametric models. And so parameter estimation for models like that is done using the maximum likelihood estimator, which we will see in a couple notebooks. And something called penalized versions of this is basically what you guys will learn in like deep learning and all sorts of algorithms that Google and Facebook use. So it's all finite dimensional. Okay. So here is some suggested steps for you to do this simulation. So now, instead of looking at the data, let's first do simulations, right? Because we want to understand what real samples from exponential lambda equals 0.1 random variable will look like, just to make sure we don't, So even if we build an estimator, we can test that it's working correctly on simulated data, right? So this is the reason why you want simulations. So here are the suggested steps. And I might turn this into an assignment. I have a couple of days, or maybe now a day. Yeah, I think it'll be good. I'll make you guys do this, right? If I say you try, I'm not going to try. So now, if you don't try, you don't get points, right? So anyway, this is a good exercise, and yeah, should be good. So here is our, oh, no. Yeah, I already gave the solution. Damn. All right, I'll change something. So this is the solution, right? Your code could be different. I might change some parameters. So here I have bus times, right? I'm using exponential sample. I have 100 bus arrivals. Actually, it should not be buses. 100 bus arrivals. Lambda is 0.1. So, and then I can simulate 100 exponential lambda random variables because we wrote all the code for this. So it's the time between buses. So how many people are waiting at the start of the simulation is 0. And then board bus initially is an empty list. Yeah, so this one's quite complicated. Yeah, so and then how many people are left waiting is the list with just those who are waiting in it, right? And then for time and bus times, so for each bus inter-arrival time, we have this loop, right? So people who arrive at the stop before the bus gets there, and then you want to add them, and then you're choosing one of the people at random to leave, and so it's a little more complicated than just waiting times, right? So you try to do this, right? Try to do this, and then the assignment will be some jazz on this. Yeah. Yeah. So anyway, this is how. So this is basically the number of people left waiting because the bus has some capacity and whatever. That's what happens in Uppsala too. The bus is too full, they don't stop, right? Except once when I lived in Sjönersta, the bus was like, it was really bad winter day. It was 2017 winter, I think. And then bus doors are completely open. People are all hanging because there was no bus for a long time. That was kind of scary. The bus was like jiggling, and anyway, sometimes, yeah. So anyway, this is just a simulation about different people boarding the bus and how long they wait, and so it can be like preparation for a following assignment here. Okay, so. Okay, so here is a solution for Cauchy running means I told you. So check it out. Now let's go into notebook 9. This is a really full-on notebook, right? I'm sort of slightly, yeah, I think we're okay. So far, what we've seen is just preparation for the main learning outcomes in the course, okay? I don't know. So this is about estimation, likelihood, maximum likelihood estimators, and regressions, okay? So the topics are like this. You know, what are parameters, what are models, and what's sort of real life. The so-called likelihood function, and there is something called the likelihood principle. It's actually it's a philosophy in some sense, because when you do inference, you are really doing something, not just so you're doing what's called an inverse problem, right? So probability goes forward, right? So it's still just an axiomatic system. You apply maths, you have a language. So when you say something probabilistically, there's no room for misunderstanding, right? So it's just like any math thing. But so probability, goes from some parameter to some law, right? So the law describes how, some phenomena of interest is distributed, right? And inference, statistical inference, goes the other way, right? So it takes observations and then tries to figure out the law. Actually, maybe I should do it this way. So theta specifies the law. So this is all very loose talk. So the theta specifies the law, and law here just means distribution, right? So there is some axis that you measure, whatever, say one dimension, and there is some kind of distribution. This is what we mean, you know, say this, I'm drawing a density, but so when theta changes, the law may change, right? So, and then the idea is now we have some observations, right? So this is say x1, x2, and x4, and so on. So a bunch of x's. And the game is now to go backwards. What is the law that generated this observation under the probability model? You see, so it's called an inverse problem. So there is, so there is a lot of there are several schools of inference and stuff. We will visit just the major classical ones, and then I will give you. Let's see how time goes. I want to give you a little bit more flavor for the machine learning course you will take as well, which is sort of more 1970s, post-1970s statistical inference. Right? So when you do character recognition, this is how the problem started in Bell Labs. Right? People are writing like letters with addresses, and then they just wanted the machine to read the numbers, the zip codes, and then automatically figure out the digits. So that's also, conceptually, that is like seeing something and figuring out what the law is. So here it's just it's a discrete law, right? Is it digit 1? Is it digit 2? And so on. But there we have to, we still use the likelihood, but we have to relax and do other things. And there's another principle called holdout estimators and empirical risk minimization principles. So these were actually developed, formalized by mathematicians working in Bell Labs at the time. Wapnick and Chervonenkis. So, okay, but that's just, I'm briefly going to touch on it, I think, but we'll do all the classical stuff here. The key idea behind the likelihood principle for inference is called the likelihood function, right? So we will look at the likelihood function for a Bernoulli theta random variable to build intuition on the simplest example and then generalize it. Revisit the New Zealand Lotto data example. And then I will show you very briefly how to use Sage Math for basic algebra and calculus. So you can use it in other courses, of course. But then you can figure out how to solve equations and do basic things. But when you're in the computer lab, I don't necessarily expect you to do everything by hand. It's sort of pointless. So you can do these things in Sage Math directly. Because, to find the maximum likelihood estimator, you have to do some differentiation, maybe twice, and you can do a lot of this symbolically sometimes. Okay, which of course means that the problems I'll give you will be much more complicated than those you could solve easily by hand, right? So that's okay. You should just be able to do it. Then we will visit the New Zealand earthquakes. Here I want to actually do some proper applied stats. So we are going to parse those files. Remember the earthquakes_small.csv file in the data folder? It had all the magnitude. So we saw just the three-dimensional plots of latitude, longitude, and magnitude. Was it yesterday? Or yeah. And then there is other fields, right? Timestamp field. So we will show you how to process timestamps in Python. So you can, at work, right? Like in Stockholm, I'm usually on Mondays in Stockholm. 80 to 90% of the time, we're just battling with just strings. I'm not kidding. It's so much. So this process is actually very underappreciated in classical academia. It's changing fast. This process is called the ETL or ELT process. It's called the extract, load, transform process. So you have to extract information from some database, right? And usually it'll be some crazy distributed database. So if you plug into Google, like Spotify's things are actually happening in Google's clouds. In Google Clouds, like 6 years ago, is public information. You have bicycle robots on single wheels moving automatically and changing broken disks as they fail and boom, boom, boom. So that's kind of the operational space, right? And of course, there's a lot of interesting number theory and distributed computing that's happening so that even if computers fail, the client will get their information fast, right? So, of course, we abstract all that. I'm not trained as a hardcore DevOps engineer or anything. But when you have access to the database, it'll be like in these forms, like timestamp formats and this and that. And so you have to kind of spend a lot of time just extracting it into the right mathematical representations so that you can do your stats and whatever, right? Modeling. So that's kind of a slight flavor of how to do this with timestamps. And then, yeah, so I haven't, I need a few hours for this. I have a lot of content on regression, but I'm trying to embed them in a nice way. So we'll probably see point estimation, which is now this idea. This is an important idea. So the point estimation and set estimation are the main types, right? So when we go and do this inversion, what are we trying to do? We're trying to estimate. So this is, estimation. And the actual algorithm or whatever you use is called an estimator, right? The estimator will take a random set of observations and produce an estimate, right? And this estimator, is usually capital theta hat because it's a random variable itself. Right? It's usually indexed by n because it depends on the sample size. And it'll produce a little theta sub n. This is called the estimate, right? Because it's its realization, right? So this estimate and estimator, there are two major ways of thinking about it. Because we only have 3 minutes left, so I'll just focus on concepts now. So one's called point estimation. So in point estimation, the idea is that there is some space where the unknown thetas live. Well, you're gonna hate me. So this is the parameter space, right? So it's a math blackboard font theta. Right? So this is the parameter space. So for our lambda random variable, the parameter space is the positive real line. So and then this is a specific theta. This is say some other theta prime. Okay. And then for each of them, we have laws, right? Each one will specify a different law, whatever. So now the goal is after you observe data, remember data lives in the data space, right? So this is our math bold font X sub n, right? So n data points live in this space. Like for images, all possible images, huge space. So now I have my observation little x, right? And this itself, let's recall, not forget this. So we have our sample space, right, where all the little omegas live. Right? Classical probability, we have events and they satisfy the axioms and so on. And so something happens and that produces this random variable x of little omega, which is little x, it's realization. Now our goal is for estimation is take this little x and go back to, theta's live here. So we go back and find the true theta. Right? Yeah, so let's say the true theta is theta star, somewhere here. And we hope that our point estimate, let's say, is theta hat sub n, lands here, right? And the game is we want to make sure that this point, just one point, is close enough to this guy, right? Especially as n goes to infinity, we want theta sub n to get closer to this, right? So this is the idea behind point estimation. And as n goes to infinity, if theta sub n hat approaches the true theta, that's specifying the law, right? So maybe the true theta star is sort of like here. And based on observations, if this happens, as n goes to infinity, this approaches theta star in some sense, right? Because this is random, right? This is deterministic. In what sense will it approach this, right? So we will get into some of these details as well in the next notebook. Then we have something called asymptotic consistency. It's asymptotic in n because n is going to infinity, right? Consistency of the point estimator. So this actually, if you think about it, what is this saying? Hey man, even if your model is right, and I'm giving you infinite information, does your estimator, is your estimator capable of recovering the true law, right? it's a very minimal requirement of an estimator, right? Point estimator. So, and that is the first property of a point estimator. And oops, okay. Yeah, there's something called set estimation. I'll come to that later. So how about Friday at 5 for assignment 2? Is that okay? Yeah. You can finish it early, you know. I mean, next Friday.